Good day, dear colleagues and students. I am going to show you physics lesson which covers astrophysics topics, spectral classification of stars. My name is Janat Amanjolовна Abишева. I am a physics teacher from НИШ Кокшетау with math and physics specialty. Our lesson objectives: understand that stars are classified by luminosity and related brightness and apparent magnitude. Describe the main stellar spectral classes. Describe the general shape of Gershon-Russell diagram and explain the evolution of a star. In this topic, we use next terminology: main sequence, Gershon-Russell diagram, gas cloud, gas nebula, planetary nebula, white dwarf, brown dwarf, red giant, supergiant, supernova, neutron star, protostar, main sequence star, black hole, event horizon, Schwarzschild radius. The reason we can see the planets is not because they give out light, but because they reflect the light from the sun. There are certainly countless other cold bodies, big and small. As we go beyond the solar system, but we can't see them since they are too far away. All the other objects we see in the sky must therefore give out light, and these are the stars. For your attention, video scale of the universe. Discover the size of our universe from Earth to the solar system and beyond. The SI unit for length, the meter, is a very small unit to measure astronomical distance. Bigger units are necessary to measure distance in space. The astronomical unit, this is the average distance between the Earth and the Sun. This unit is more used within the solar system. One astronomical unit equals 150 million kilometers, or 1 AU equal 1.5 times 10 in power 11 meter. Next video, what is the light year? When we look at a distant star, we are looking back in time. What is the light year? How is it measured, and why do we measure distance in terms of time?
Nothing can travel faster than the speed of light. It moves through space at 300 million meters per second. Astronomers use light years to measure the enormous distances in space. Using meters or even kilometers just isn't practical. Although light travels very quickly, distances in space are vast. It takes 8.3 minutes for light to travel from the Sun to the Earth. This means we don't see things as they happen. A sudden change in the Sun's brightness would take 8.3 minutes to be visible on Earth. Our nearest star after the Sun is Proxima Centauri, which is 4.2 light-years away. When we see it at night, the light we see actually left the star 4.2 years ago. Despite the speed of light, the vast scale of our solar system means that when we look into space, we're actually looking back in time.
In astrophysics, the following distance units are used. Light year, this is the distance traveled in a vacuum by light in 1 year. Astronomical unit, this is the mean radius of the Earth's orbit around the Sun. One astronomical unit equals 1.50 times 10 in power 11 meter. Parsec, this is the distance in which the mean radius of the Earth's orbit has an angular displacement of 1 second. 1 divided 3,600 degree. 1 parsec equals 3.26 light year, equal 2.06 times 10 in power 5 astronomical unit, equal 3.09 times 10 in power 10 meter. The light year, this is the distance traveled by the light in 1 year. We know the speed of light equals 3 times 10 in power 8 meter per second. Time, 1 year, 365.25 multiply 24 multiply 60 equals 3.16 times 10 in power 7 second. Speed equal distance over time. Distance equals speed multiply time. So distance equals 3 times 10 in power 8 multiply 3.16 times 10 in power 7 equal 9.46 times 10 in power meter. In main unit in astronomical distance is parsec. Parsec is short for parallax arc seconds. The parsec, the distance at which one astronomical unit subtends an angle of 1 arc seconds. 1 parsec equals 3.086 times 10 in power 16 meter, or 1 parsec equals 3.26 light year. The parsec is defined in terms of the angle subtended at the star. If the distance to a star is 1 parsec, the angle subtended will be 1 second. This makes calculations much easier since the distance in parsec is simply 1 over the angle in seconds. Review. Units of length. Astronomical unit. 1 astronomical unit equal 1.5 times 10 in power 11 meter. This is the distance between the Sun and the Earth. Light year. 1 light year equal 9.46 times 10 in power 15 meter. This is equal to the distance traveled by light in 1 year. Parsec. 1 parsec equal 3.26 light year. This is defined the making a triangle between the Earth, the Sun, and a distant object. If the angle at the distant object is 1 arcsecond, then it would be 1 parsec away. For your attention example, the smallest angle that can be measured between light rays that arrive at the surface of the Earth is 0.01 arcsecond. What is the distance to a star that subtends this angle? Solution: D equal 1 over 0.01 equal 100 parsec. The first objective of our lesson: understand that stars are classified by luminosity and relate brightness and apparent magnitude. The reason we can see the planets is not because they give out light, but because they reflect the light from the sun. All the other objects we see in the sky must therefore give out light, and these are the stars. For your attention, next video: Sun. Our Sun is a medium-sized star which creates the perfect conditions for life on Earth. What happens on the Sun and how do stars, including the Sun, live and die? The Sun is a stable star. This means that it isn't getting bigger or smaller. The mass of the Sun is so large that the gravitational force experienced by the outer layers is very big. This alone would cause the Sun to collapse. The reason it doesn't collapse is due to the continual production of energy from the fusion reaction in its core. This gives the particles kinetic energy, causing a pressure, radiation pressure, that push back against gravity. We can compare this to a balloon. The rubber of the balloon pushes in and the gas pressure pushes out. A balloon doesn't need a source of energy because its temperature is the same as the surroundings, but if it lost heat, the inside pressure would drop and the balloon would shrink. Since the Sun is losing energy all the time, it needs a source of energy and remains stable. The reason we can see the star is that they give out light. By measuring this light, we can gain a lot of information about the temperature, size, and chemical composition of the star. The main characteristic of the star: luminosity. Luminosity notation L. A measure of the total visible radiant energy a star emits per second. energy emitted uniformly in all directions. The unit of luminosity is watt. Our sun luminosity equals 3.90 times 10 in power 26 watt. If two different sized stars have the same temperature, the bigger one will give out more energy than the small one. If you look into the sky at night, you will see that some stars are bright and some dim. The brightness depends on how much light is entering your eye, and this depends upon how much light the star gives out its luminosity and how far away it is. If you look at two identical stars, one close and the other far, the closer one looks brighter because the light hasn't spread out so much. Apparent brightness, next characteristic of star. The definition, this is brightness notation is B. This is illustrated in figure. When the light from the sun reaches the earth, it will be spread out over a sphere of radius d. The apparent brightness is related to the luminosity by the equation B equally L over 4 pi d squared. The energy resolved per unit time per unit area, where B is called the apparent brightness of the star. Brightness notation is B. In the figure, you see surface area equal 4 pi d squared. As the light travels away from the star, the energy is spread over a bigger area. Apparent brightness notation B. The energy resolved per second per unit area at the Earth. Essentially, this is a measure of the brightness we see here on Earth. Can be measured by attraction and radiation sensor light meter to a telescope. Important. The brightness of a star is not necessarily an indication of how far it is from Earth. Unless we know a star's luminosity, it is impossible to determine distance simply based on the measured apparent brightness. For your attention tasks. Task 1. The sun is 1.5 times 10 in power 11 meter from the Earth. Estimate how much energy falls on a surface on 1 meter square in a year. We know sun's luminosity equals 3.90 times 10 in power 26 watt. Solution. At distance equal 1.5 times 10 in power 11 meters, the energy is distributed along the surface on a sphere of radius 1.5 times 10 in power 11 meter. The sphere's surface area is given by area equal 4 pi d squared equal 4 pi multiply 1.5 times 10 in power 11 squared equal 2.83 times 10 in power 23 meter square. The energy that falls on a surface area of 1 meter square on Earth per second will be equal to luminosity of sun over area equal 3.90 times 10 in power 26 over 2.83 times 10 in power 23 equal 1378.1 watt per meter square, or 1378.1 joules per second meter square. In a year there are 365.25 days, multiply 24, multiply 60, multiply 60 equals 3.16 times 10 in power 7 seconds. So the energy that falls in 1 meter square in 1 year will be 1378.1 multiply 3.16 times 10 in power 7 equal 4.35 times 10 in power 10 joules. Next task, task 2. Looking at the spectrum of light from Betelgeuse in the constellation of Orion, its peak wavelength is it 9.35 times 10 in power minus 7 meter. What is the surface temperature of Betelgeuse? Lambda maxima multiply T equal 2.898 times 10 in power minus 3. T equal 2.898 times 10 in power minus 3 divided by lambda maximum. T equal 2.898 times 10 in power minus 3 divided by 9.35 times 10 in power minus 7 equal 3100 Kelvin. Next task 3. The period of a Cepheid variable is 10 days and its brightness 1.0 times 10 in power minus 10 watt meters per meter square. How far is it from the Earth? Solution. The luminosity of Cepheid variable with period 10 days is 3000 of Sun's luminosity. The luminosity of the Sun is 3.839 times 10 in power 26 watt. So this star has luminosity 3000 multiplied 3.84 times 10 in power 26 equal 1.15 times 10 in power 30 watt. Is 3.839 times 10 in power 26 watt. So this star has luminosity 3000 multiply 3.84 times 10 in power 26 equal 1.15 times 10 in power 30 watt. Rearrange B equal L over 4 pi d squared gives d equal 5.5 times 10 in power 18 meter or 584 light year. Next objective of our lesson, objective 2. Describe the main stellar spectral classes. How bright is star? Observing stars with the naked eye, we are only able to distinguish 6 different levels of stellar brightness. Astronomers have classified stars into groups according to their temperature. This is useful property to use sense star with similar temperature tends to share many other features. The temperature determines the spectral output of the star, but it can also suggest chemical composition and age. The spectral star classes are labeled by letters: O, blue; B, blue and white; A, white; F, yellow-white; G, yellow; K, orange; M, red. Next objective, objective 3. Describe the general shape of Hertzsprung-Russell diagram and explain the evolution of the star. For your attention, video, what are stars? What are stars made of? How are they born? How do they live? And how do they die?
Our nearest star is the Sun. But our Sun is only one of countless billions of stars in the universe. Just like us, stars are born, age, and die. They are formed from clouds of dust, hydrogen, and helium gas, which shrink under gravity and heat up to make a star. Astronomers group stars by age and size into 3 main types. 90% of stars, including our Sun, are in a group called the main sequence. Main sequence stars are in a stable stage of life. They're fueled by nuclear fusion of their core, converting hydrogen into helium. When stars age, they become part of the second group, known as giants. Giant stars have swollen in size because their hydrogen supply is running out, and they now use helium for their nuclear reactions. As a result, the core shrinks and becomes hotter. The star generates new elements, such as carbon and sulfur, which make the outer part of the star bigger and cooler. Then, depending on the size of the star, 2 things may happen. Red giants will become planetary nebulae as their outer layers continue to slowly expand. If their cores remain as stars, they will become part of a third group called white dwarfs. These are initially very hot, but will eventually cool to become cold black dwarfs. Supergiant stars, however, will die and explode as supernova, releasing as much energy as the Sun gives out in 10 billion years. The surviving stellar core will become either a neutron star or a black hole. All the star's elements are blown out into the universe within the expanding shell of the supernova. These elements become the building blocks of new stars and planets. And so it's the death of a star that creates the conditions for new stars to be born.
You will see from that during its life, a given star develops along a sequence from the one type of star to another. If you observe it at each of these points in its life, they would be plotted in different places on the Hertzsprung-Russell diagram. Thus, we can plot the life cycle of a star as a movement around the HR diagram. Stars are formed when large clouds of gas and dust begin to collapse due to their own gravity. As the dust accelerates towards the center, it drains kinetic energy, movement energy. As the dust cools and comes to a halt on the center of the cloud, this energy is converted to heat through friction, and the temperature of the dust increases. When the core temperature becomes high enough, nuclear fusion begins to occur. At this point, the collapse is halted and is released from the core of the new star. The life cycle of a star varies depending on the mass present at the star. However, in general, throughout most of their lifetimes, stars will burn hydrogen to make helium. Eventually, the star its supply of hydrogen. It is more difficult to achieve fusion with helium, and so the star cools as fusion shuts down and gravity begins to dominate, pulling material towards the core. Soon the core is compressed sufficiently for helium fusion, and helium flash may occur. The energy release is much greater than the from hydrogen fusion, and the outward force begins to dominate, pushing the material further away from the core. This causes the star to smell and become giant. The star with very low mass will never be able to fuse helium, and so will continue slowly burning hydrogen until it collapses. We do not know for sure what happens to stars like these, as the universe has not existence long enough for any of these stars to complete their life cycle. In next video, black holes. Discover how giant stars transform into black holes, a race of mass so great that even light can't escape.
When a massive star dies, it's believed something truly terrifying is born. A black hole. When a star burns, nuclear reactions are taking place inside its core, creating an outward force able to balance the inward force of gravity. When it runs out of fuel, this outward force disappears, and the core of the star collapses in on itself. When the core has a mass greater than about 4 times that of our Sun, it's condensed into a single point, smaller than the size of a pea. This is called the singularity. As this happens, the surface layers of the star blast outwards in a supernova explosion. What's left behind is the black hole. The gravitational pull around the singularity is enormous. The force close to it is so strong that not even light can escape. This region is called the event horizon. Anything inside this area will be pulled towards the singularity and lost forever. The event horizons of many black holes are surrounded by an area of hot infalling gas called an accretion disk. If the disk is spinning rapidly, some of its matter can be shot out into space at incredible speeds. It's propelled along the powerful magnetic field which the disk generates, creating colossal jets of radiation. Black holes are among the most violent and fascinating phenomena in the universe, but their destructive reputation is greatly exaggerated. They don't devour everything around them. If the Sun was replaced by a black hole with the same mass, the Earth and other planets wouldn't suddenly be pulled into it. They'd continue to orbit around it in the same way that they orbit around the Sun. It's thought that there is a supermassive black hole at the center of the Milky Way, with perhaps hundreds more lower mass black holes lurking throughout our galaxy. But these will only be a threat to us if our paths happen to cross. This is unlikely to happen anytime soon, as the nearest black hole to be detected so far is 1,600 light-years from Earth. More than 3 million times further from us than Neptune.
During the lesson, we progressed from I know to I can. For your attention, extension question. How are stars formed? How do stars change? How do stars die? What's a neutron star?
How do stars die? Eventually, the star will consume its helium and will begin burning carbon. Carbon burning proceeds very quickly as particles called neutrons are produced, and these neutrons interact with the material in the star. These escape from the star taking energy with them, resulting in a higher rate of energy loss. Gravity also begins to dominate again and compresses the core, which results in a higher rate of burning, which maintains the size of the star.
Stars formed. Stars are formed when large clouds of gas and dust begin to collapse due to their own gravity. As the dust accelerates towards the center, it gains kinetic energy. As the dust collides and comes to a halt at the center of cloud, this energy is converted to heat through friction, and the temperature of the dust increases.
How do stars change? The life cycle of a star varies depending on the mass present at the star. However, throughout most of their lifetime, stars will burn hydrogen to make helium. Eventually, the star exhausts its supply of hydrogen. It is more difficult to achieve fusion with helium, and so the star cools as fusion shuts down, and gravity begins to dominate, pulling material towards the core. Soon the core is compressed sufficiently for helium fusion, and a helium flash may occur. The energy released is much greater than that formed from hydrogen fusion, and the outward force begins to dominate, pushing the material further away from the core. This causes the star to swell and become a giant.
What is neutron star? Neutron star can form after the supernova. They have a mass around twice of the Sun and diameter of 20 kilometers.
Your home task. You must do solution 3 tasks. The first task, you calculate its appearance brightness of the Sun and brightness at the distance of 10 parsec. The next task, you can calculate the appearance brightness of Sirius and brightness at a distance of 10 parsec. The third task, you can calculate the distance from a star to the Earth in light year. The resource for lessons: Chris Hamper and Twig Blim KZ. Thanks for attention.